Okay, welcome back. So let us start with the Jacobian method. This will be quite simple approach in order to remember the Maxwell relation as well as to apply to obtain various different thermodynamic relations. So efficacy of such a method corresponding or with respect to the one which is based on just derivatives. So let us consider x is equal to x OAB and y is equal to YAB. So what I am going to do now is to just write down the properties of this Jacobian method. Okay. So the Jacobian is defined as follows. Okay. And essentially this is nothing but the determinant of del x by del A, del y by del A, del x by del B and del y by del B. Okay. So this I can further write as del x by del A, del y by del B minus del x by del B, del y by del A. Okay. So many times is written or one can show that the J is sometimes it's written as simply x y a b. It can be shown as this is nothing but this. Okay. So without going to the derivations in details, I am going to just write down some of the properties of Jacobian, and this comes directly from the knowledge of determinants, okay, or the properties of determinants. So Jacobian has the following properties. Important properties. Okay. So okay, you may ask question, what does this particular mean? So this would be more like a differential of x keeping x constant, or differential of x keeping y constant, and essentially this is directly related to the determinant approach. For example, in this case, if I had replaced this by b, okay, a by b, by considering such that y is b, then this essentially means del x by del a by b. Now this you can prove it using this. Okay, so you can plug in this and essentially you can show that. Okay, this is indeed this expression from the Jacobian expressions, you can derive it. Okay. So without, as I said, without going to the details, we are going to write these expressions and then we will make use of it in our thermodynamic derivations. So x of z, y of z is nothing but del x by del y keeping z constant. For convenience we write it in this way. Okay, it's easy for us to make use of our analysis. So for the case of this x y a b and a b, so the a b get cancelled, so this is nothing but x y this. Okay, so these are the properties here. Now how do we use it? So let us try to do some examples here. So let's say consider z is equal to function of x and y, and we would like to take the z into differential form dz, which I can write is in the following way. Now here what I would like to do is I would like to represent this expression, the partial derivatives, in the form of Jacobian. So this is nothing but z, y is constant here, y is basically kept constant, so I can write this as okay dx plus z x y x okay dy. Here of course we know that x y is nothing but minus of y x, so hence if I multiply this x of y dz, I get zy dx minus zx dy. Okay. Now, from here I can also obtain cyclic relation. So, if I consider this and let us say take a partial derivative of this with respect to b, I can write actually the following: zb, and if you rearrange here, plus this is equal to, so if you bring it to the other side, I can write it like this: x of b plus z of x y of b, and this must be equal to 0. So, this is nothing but cyclic relation. Okay. So, if you apply this thing for thermodynamic potentials in the derivative form such as T ds minus P dv, so I can clearly write this as u as a comma x, x could be any variable if you want to differentiate, T x minus P v x, okay, where x is basically dummy variable. Okay. Now, similarly, I can do the same exercise for h. Okay, dh is T ds plus v dp. I can write this as h x is T s x plus v p x. Okay. Similarly, I can do that for other variables. Now, let us apply this concept of Jacobian to the Maxwell relation and see what kind of expression we get when we apply to Maxwell relation. Okay, so let us start with the first Maxwell relation. Okay, so I am going to write this as del v by del s, p is equal to del t by del p s. So, this is the first Maxwell relation which we have. Now, I would like to see how this will yield, what kind of expression it will yield if we apply the Jacobian method. So, Jacobian method, if you apply, this is v. So, this will be your v p s p, and this is your t s and p s. Okay. Now, we know that s p is nothing but minus of p s. So, hence this would mean that v p is equal to minus T s, right, because this will cancel out with a negative sign here. So, this will be minus here. Now, or I can write this as T s is nothing but P v, okay, or I can write as S t is nothing but V p. Okay. So, these are equivalent, right. Okay, so I have one relation now from this particular Maxwell relation in terms of Jacobian. Let us look at the second one, del v by del t at constant p is equal to minus del s by del p at constant t. So, this is going to be V p T p okay. So, again you can cancel out this, and with this you can get rid of this negative sign also. So, what you have is V p is S t is nothing but this one, right, same expression we obtained. Let us look at the third relation. Okay. So, this cancels and this negative sign comes here, and this if you rearrange here, this will be your again S t is equal to V p, same as this expression. Okay. So, all the three Maxwell relation yielded the same expression. Let us look at the final Maxwell relation we have from these fundamental relations. So, this is same with negative sign. So, hence this becomes positive. This yields Ts is equal to Pv or St is equal to Vp, same relation. So, it turns out that all the 4 Maxwell relation yielded the same in the form of a Jacobian variable. So, finally, one can summarize that Maxwell relation is in Jacobian expressions is just one expression, that is Ts is equal to Pv. You do not have to remember actually 4 expressions, you just have to remember just one in Jacobian, and that solves the problem significantly. So, how do you adopt the method of Jacobian in solving thermodynamic problems as well as the relation, the derivatives which we have to evolve or derive. Now, one can write down a summary of this kind of a procedural form. So, the following procedure can be adopted, may be adopted. So, express the required partial derivative in the Jacobian notation. So, that will be the first step. The second step is if any notation or Jacobian expression contains only one of the thermodynamic function or potential, that is U, A, H and G, they may be eliminated by substituting from thermodynamic fundamental equation. So, that is point number 2. Point number 3 is if contains 2 thermodynamic function or thermopotential potential, it can be reduced to expression having only one potential by substituting or by making use of the cyclic relation. So, in such case you have to use the cyclic relation. Now, fourth, if the notation or expression contains entropy S, then it can be eliminated by using Maxwell relation. Ts is equal to Pv, or use Cp or Cv. If any notation contains Pvt, then you can eliminate that by using beta and kappa. Finally, if chemical potential comes in, use Gibbs-Duhem equation. So, this is something which one can summarize how one had to use the Jacobian in order to solve problem. So, before I close this session or lecture, let me try to solve a final example using both the methods, the method which is partial derivative ones and the other one is a Jacobian method. Okay. So, you have to derive this expression. So, the first which we will try is partial derivative based. So, here of course, I can clearly see is that S is a function of STP. So, I can write ds as del S by del T at P dt plus del S by del P at T dP. So, this is what I would start with, because you are interested in this expression and this appears to be a function of T and P. And now, I can replace this by because this is at constant pressure, the derivative S with respect to T, which is nothing but Cp by T. Okay. And then this is the term where we have to get some Maxwell relation, because we have to replace this. So, I may use a bond diagram. So, S V T P, and since I am interested in this S and P, essentially I am going to look at this side. Okay, of course, this has to be in this way. So, if I look at this side, then essentially this can be replaced as minus. So, that this is del V by del T, del V by del T at constant P, but since this arrow is pointing towards itself, so there has to be minus sign, and this is dP. So, I am using this bond diagram to get that. So, this and this now further can be simplified by making use of, because PVT and I have to use beta and kappa. So, beta is 1 by V del V by del T at P. So, this is nothing but beta V, right. So, I have now expression Cp by T dt minus B beta V dP, okay, or TdS is Cp dt minus T beta V dP. Okay. So, this is from your partial derivative approach. Now, how you do that, or let us see how we do when we make use of the Jacobian. So, now looking at this expression, again we go back to this expression. Okay. So, this we have the partial derivative, we have to represent the partial derivative with respect to Jacobian notation, and this is what I have written here also. Okay, express the required partial derivative in the Jacobian notation. So, let me do that. This is going to be Sp partial derivative of S with respect to T at constant pressure okay. So, this is the expression del S by del T, that means S comma P divided by bracket at T comma P. So, that is the definition of the Jacobian. So, this is what we are going to write it here. Now, this we know anyway, this is a Cp by T, okay, there is nothing great about that, but what about this? Now, we have to replace S. Now, we know the Maxwell relation. Maxwell relation for this is straightforward, St is nothing but Vp. So, remember that St is nothing but Vp. Okay. So, I have got this relation straightforward. I do not have to worry about the bond diagram or anything else. Now, this Vp, if you replace this sign rather in here P, then I can get negative sign here. I can write P and this is T P. So, this is nothing but del V by del T at constant pressure, and this is something which we can now replace by beta V. Okay. So, you still have to remember the definitions of the beta and K's and Cp and Cv, that is necessary, and in addition of course, you have to remember or you can derive this on the fly, the thermodynamic functions, but otherwise there are two different approaches which you can make use of it to calculate the derivatives or the expressions of thermodynamic functions. So, I hope that I have given a comprehensive way to solve problems in the thermodynamic property relations, making use of the partial derivatives Jacobian and the definitions of Cp, Cv, alpha, kappa. This would help perhaps you will see that later part you will be using this, and of course, with the help of some certain assignments you will also practice, and hopefully you will gain the solid foundations for using these expressions, this understanding to derive derivations for complex expressions as well. Okay, so I think I will stop here, and in the next lecture I will move to equilibrium, stability, and other kind of concepts. Okay, so I will see you in the next lecture.